message first. Okay, you're recording. Fine. So let's look at what we have done last time. Minimize that as well. All right. Last time we talked about the simple cubic crystal structure, the base center cubic, the body center cubic crystal structure, and the face center cubic crystal structure, the SC, the BCC, and the FCC crystal structures. Today we will continue talking about the hexagonal close pack crystal structure. Now, the hexagonal close pack crystal structure is quite different. The name is hexagonal close pack crystal structure. So you have HCP, and that is the short form, the HCP, which stands for hexagonal close pack crystal structure. Hexagonal close pack, of course, from the name, from the word hexagonal, so it's not cubic. And the rest we have seen simple cubic, face center cubic, body center cubic. Here we don't have the cubic crystal structure. It is basically a hexagonal prism, the shape which we are showing here. These are the lattice positions of the atoms in the hexagonal prism. One thing I just wanted you to reply. Are you hearing me well? Are you with me?
Yes, Doctor.
Yes, Doctor.
Okay, shukran. So this is a hexagonal prism, as you could see there, and the shape is completely different from the cubic crystal structure, in that you have 6 corner atoms in the hexagon, making a hexagon there on the top, and another 6 also atoms in the corners, as you could see there, 1, 2, 3, 4, 5, 6, making a hexagon as well there. You have 2, actually 1 here, a phase atom in this phase, and another phase atom coming there as well, in addition to 3 internal atoms making this triangle, as you could see down here. So this is basically how the hexagonal close pack crystal structure looks like. This is the atom in the atoms in the lattice distributed. Normally, of course, it's very difficult to draw this. We normally draw the lattice positions of the atoms for the different crystal structures we have. Now, in order to look at the coordination number, what is the coordination number of this hexagonal close pack crystal structure? So we basically simply look at one atom, we choose one atom, and we see how many atoms are touching that atom. The simplest atom that I could be looking at will be this atom actually. It makes life very easy. We look at this atom, we see how many atoms are touching this atom. From that surface, from this layer, from this plane, you can see the atoms touching are these 6 atoms there. This, and that, and this. These all 6 atoms are touching this atom. In addition to these 6 atoms, these 3 atoms at the bottom here are also touching. This is touching this from that side. This is touching from this side. This is touching from the spaces which are there. So in addition to 6 atoms here, you have 3 atoms also touching from the bottom. In addition to that, there are another 3 atoms there. Yani, because this is how it goes. This is the hexagonal unit cell. The hexagonal close pack crystal structure unit cell has 3 atoms here, and then a hexagon here, and then again 3 atoms here, and then a hexagon here. So imagine you have another unit cell there, a hexagonal prism also having there. So you have that face atom is shared between this unit cell and the unit cell above. So above that will come what? So these corner atoms are shared by this unit cell and the upper unit cell. This face center cubic, this is and it's in the face, so we call it face center atom. So it's shared by this unit cell and the upper unit cell. Now above that, there are 3 atoms coming here. In the same way, this is there. And above that, the 3 atoms, there is a hexagon. So Therefore, there are another 3 atoms there. These 3 atoms are also touching this atom. So therefore, we have how many atoms then there? We have 3 atoms here. We have 6 atoms here touching this atom, and 3 atoms from the top also touching this atom. 3 plus 6 plus 3 total will become how much? It will become 12. Notice the coordination number of the hexagonal closed pack and the FCC crystal structure is the same. In the FCC, we also notice that we have 12. The coordination number was 12. Here also we have 12. In addition, also some other similarity to the face center cubic crystal structure is that if we calculate the atomic packing factor, we will also find it to be 0.74. Remember, in the FCC crystal structure, we found it, we calculated that basically using the calculation, we found it to be 0.74. Here also, the atomic packing factor will be 0.74. I'm not going to derive that. It's much more complex than the cubic one. The lattice parameters are not the same. We have A and C and other parameters there. It's lengthy, that's why I don't want to do it in the class, and I will not require you to do that also. But it's just algebra and geometry that we want to use. But I'm not going to do that here. But there is one thing which we want to do actually, which is the number of atoms per unit cell. Remember, here we all needed the number of atoms per unit cell to calculate the APF. Also, we need that to calculate the number of atoms per the APF here as well. But also, atomic packing factor is required in order to calculate other things, like the theoretical density, for example. So that is simple. I'm going to look at, because in this one, it is different also. The number of atoms per unit. The number of atoms per unit cell, N, which we have used before, is equal to Ni, which we said, right, plus Nf over 2, remember that, over 2, plus N corner, remember, N corner over how much? Yalla gululi, aina nasit. I forgot how much?
8.
8, right?
8.
In the cubic crystal structures, we did look at this, and we remember that we explained it here. We said that it's 1/8 of an atom, right? And that's why in the formula it's divided by 8 here. You see? So that's why number of corner atoms divided by 8 comes from there. That every corner atom is 1/8 of an atom. That's why we used in the formula 1/8. 1 over divided by 2 for the phase atoms, because any phase atom there, well, not here, here for example, any phase atom divides into 2 unit cells. One, this atom is divides into this unit cell and the neighboring unit cell, which is just beside it. So that's why we divide the number by 2. This is how the equation is. Internal atoms, all of the atom will be inside. This is an internal atom, and that's why when you say Ni, we say it just Ni, because all the atom will be inside there. Now for the hexagonal closed pack, that corner atom divides differently than the cubic one. So if we want to look at that, very simply, we can draw very simple continuation to the unit cells that we have here. Suppose we have that neighboring unit cell, which is here. I'm going to draw as much as I can. So that is another unit cell. And from here also, you have another unit cell here as well. There. And
2.6 لا
ها ايوه بس ابي اراويكم
نقسم على 6
ممكن في ناس ما يعرفون. Okay, so we have another unit cell. So As you could see there, this is one unit cell, this is another unit cell, and this is a third unit cell. If we look at this atom now, how many unit cells are sharing this atom? This atom is being shared by how many unit cells? The lower
6.
The lower part of the atom is being shared by the lower part is being shared by this unit cell and this unit cell and that unit cell. But the upper part of the atom also is being shared by the unit cell which are at the top. There are other unit cells there. صح ولا لا? And there is another unit cell above this one, and so on and so forth. So the upper, and from here as well. So the upper unit cells there, the 3 unit cells at the top of these 3 unit cells share the upper part of the atom, and the 3 unit cells down share the lower part of the atom. So therefore, basically, this atom is being shared by how many unit cells? 1. This is 1, 2, and 3. And above this one is 1. Above this one is 1. Above this one is 1. So totally, we have 6 unit cells are sharing this atom. So therefore, the part of the atom which is inside, the corner atom which is inside this unit cell is actually 1/6 of an atom. It's not 1/8 like what we have in the cubic crystal structure. Therefore, what we do is that we divide that, instead of by 8, we divide it for the hexagonal close packs by 6. So if we want now to calculate the number of atoms per unit cell, what is it equal to? Okay, so let us look at the, let me erase all that. When the eraser, I think here. So let me erase all that. So let us look so that it will be clear how to do that. Okay, fine. Now let us calculate how many unit cell pen. How many number of atoms per unit cell? Do we have internal atoms? Of course we do. 1, 2, and 3. So we have 3 internal atoms, plus how many phase atoms do we have? That is one phase atom here, and this is another phase atom here. So we have 2, so that is 2, and it is shared actually by other unit cells. So 2 divided by 2. Plus, how many corner atoms do we have? This is 1, 2, 3, 4, 5, 6. That's it. We have 1, 2, 3, 4, 5, 6. So 6 plus 6 is equal to 12. So this makes 1 over 12 divided by 6, because each is 1/6 of an atom. If you add those together, 3 plus 1 is 4, plus 2 is equal to 6. So that is the number of atoms per unit cell which we are calculating here. So the number of atoms per unit cell you can calculate for the simple cubic, for the body center cubic, for the face center cubic, and for the hexagon crossback as well. We need this number in calculating many things, physical properties like the theoretical density, which we will be looking at next. Examples of materials which display this crystal structure types, like the magnesium, the zinc, the titanium, the cadmium, the zirconium. These are all examples of materials which display this type of crystal structure. You already have the book. If you don't have it, I already sent it to you from the beginning of the semester. Not for commercial purposes, طبعا. It is available online to you, and we are recording here. And in the inside part of the cover of the book, you will find a table. That table consists information about metals, and we are concerned about metals here, not about all materials there. All the metals, which are the famous metals which are there, atomic number is given, You have also what is given there, the crystal structure type for all the metals which are of importance to us, like the ones that we have covered already, and these as well. You will find all the type for all those metals, the type of crystal structure there. So I urge you to go and have a look at those. At the end of the day, you need to know. It's only fair to say here, you need to know examples of materials which display, specifically the ones that we have covered in the class. You need to know them. What type of crystal structure do they display? How to calculate the coordination number or get the coordination number for these four type of crystal structure we have covered. The number of atoms per unit cell for these four types of crystal structure that we have covered. Calculate the atomic packing factor for the three first one, and for the hexagonal close pack you need to know the number at least. You are not required to do calculation. And you need to know the close pack directions as well. Not to forget what are the close pack directions in the hexagonal close pack crystal structure. These are basically the close pack directions. Atoms are touching in these directions. So this is where these are the only close pack directions in the hexagonal close pack crystal structures, and due to the very little number of close pack directions there, you have, or I would say the planes basically. That's why these materials are brittle materials, actually very hard materials there. So with this, we want to continue with the hexagonal close pack crystal structure. One note that we want to make, I already noted that the FCC and the HCP crystal, both of them have 12, have the coordination number is 12, and the atomic packing factor is 0.74. This is actually the maximum packing factor that could be in any metal. There is another thing which is different, or other things which are different in these two different crystal structures, like the stacking sequence, for example. If you notice, this is the hexagonal close pack crystal structure. We have the hexagon phase, which we have here, which we refer to as A site, and then we have the triangle site, which we call B site, and again we have a repeating A site here, the same as that is repeating there as well, and it continues like that. Below that we have another B site coming here, and then after this you have another A site. So this is what we refer to as, this is actually a three-dimensional projection we are looking at. This is two-dimensional projection. So you have the top layer, the middle layer, and the bottom layer, and then the bottom layer is the same as the top layer, and then it continues in the same way. So this is what we refer to as a stacking sequence of AB, 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 AB in the material in this direction. So we already looked at the coordination number and atomic packing factor is the same in the HCP crystal structure with and the FCC crystal structure, but the stacking sequence is completely different. In the FCC crystal structure, the sites, this is the 2 dimensions projection. Actually, if you look at the top, but it's easier to look at the 3-dimensional. This is the crystal structure. Notice that we have we have for the parts or the planes that we have there. For example, if you start from here to there and then to there, this is one plane that you can make there. Here, this mouse that I'm having, another plane will be from here to there and to there, and another part which is this atom which you have here. So this basically we have one plane and then the other plane here and then this, and this repeats in the crystal structure of the FCC crystal structure. You have that plane, and then you have this plane, and then you have that atom. And you could see it maybe more clear here. You have the green plane at the back, which is starting from this point here, the green plane, and then the blue plane, as you can see there, and then the atom C, which you have. This actually sequence continues, but of course this is in the direction of the diagonal. There it is in the longitudinal direction. This is in the direction of the diagonal. It continues like this. Stacking, it has a stacking sequence, but the stacking sequence is A, B, C. It's not A, B, A, B. So it's A, B, C, and then A, B, C again, and then A, B, C again, and continues like that. A more clear 3D. So that is the first plane that I'm showing here. That is this plane. This is the one. And then in the cube, you have another plane here. And then you have that atom. So in the direction of the diagonal there, it continues. You have a stacking sequence of A and B and C. And then the next one, in the next crystal structure, again, we will have A and then B and then C. And it continues in that way. A, B, C, A, B, C, A, B, C. So the stacking sequence is quite different in the face center cubic crystal structure than the hexagonal close-packed crystal structure. That's on one big difference there. And another thing is that the number of planes actually which makes the number of planes which makes the the number of planes or the number of close-packed directions here. This is a close-packed direction, and this is a close-packed direction, this is a close-packed direction, this is a... The number of close-packed directions that you have is much bigger than the number of close-packed directions which you have in the HCP crystal. In HCP crystal structure, all those actually make one plane. But the number of planes here in the FCC crystal structure are many, are much greater, and that's why the FCC crystal structures are much softer than the HCP crystal structure. The HCP crystal structures are much more harder. So as you can see, the magnesium or the zirconium are brittle, while if you look at the FCC crystal structure, for example, aluminium, nickel, copper, silver, platinum, and gold are much softer. Their strength is also less actually than those. This is how it goes. So I'm showing the difference between them. Next, I want to look at how we can use the knowledge of crystal structure to determine some physical properties of the material. I mentioned already that we can determine the theoretical density. If you want to determine the density of any material, you need to go to a lab and you need to use apparatus and then get the volumetric cylinder and water, for example. If it is an irregular shape, for example, if it is regular, then you can calculate, you can use the scale and get the weight, and then you can measure the volume. From that you can get the density. If it is not regular shape, then you need to get the volume from the cylindrical, from the volumetric cylinder. So you need to go to the lab and do these measurements. But a knowledge of a crystal structure also permits the calculation of theoretical density. And let us look at how we can calculate the theoretical density and how does it compare to the experimental values that we get from the lab. The theoretical density is equal to basically the number of atoms per unit cell times the atomic weight of the element divided by the volume of the unit cell of the crystal structure times the Avogadro number. Avogadro number is known, so that is something that we know. The atomic weight, we get it basically from a table. It's available in all tables there. So we need to get for any metal, for example, because we are concerned with metals here, we get the number of atoms per unit cell, which I told you is important quantity in a lot of calculations. So we need to get the number of atoms per unit cell, and we need to get the volume of the unit cell. We get these two, then we can determine the density, the theoretical density. So let's go here. I'm putting the equation also here in order to ease the issue. So let's say, for example, as an example, we want to determine the theoretical density of copper. Of course, if I tell you determine the theoretical density of copper, I would give you the information, for example, the atomic weight, which we already said. This is you can get from the table, or I give you a table with the atomic weight, and I give you also the Avogadro number here. I will give you that as well. And I mean, the table normally looks like that. This table is available in your book as well. Let's say for copper, for example, that's the symbol of copper. The atomic weight is given to you. And also something else would be given to you, which is the atomic radius. The atomic radius here has a unit, as we have here, which is nanometers, right? So we are getting the atomic radius as well. The radius of the atom, basically, it is 0.128 nanometers. So from that table, but obviously I wouldn't give you that. And this you wouldn't see that as well in the information I would give you, because this is the density, experimental density we get, and that you need to know. For copper, for example, you need to know copper has an FCC crystal structure. So to solve the problem, first of all, we say the copper has an FCC crystal structures. So for FCC crystal structure, what is the number of atoms per unit cell? Well, basically we say N is equal to Ni plus Nf over 2 right, and F, let's get it correctly, plus Nc over how much? Shabab, على كم?
8.
How much should I put? 8 or 6? 8, صح? This is cubic, face center cubic, right? So for the face center cubic, are there any internal atoms? No, of course, there are no. So that's 0. Do we have phase atoms? It is called phase atom. So every phase in the cube has an atom. So we basically have 6 phases in the cube. So this basically is 6, right? And then we have corner atoms. It is a cubic. It is cubic. So there are يعني الحين صعب انك تحفظ ان كيوب فيه 8 corner atoms وصعب انك تحفظ ان الكيوب فيه 6 phase atoms. Am I saying something difficult to know? It's very simple.
قصدي المادة معاهم لازم نحفظهم
أنا قلت الكلام ده. المواد whatever metals، مو كل المواد في العالم يعني. The metals, we are concerned with metals, that I said already that, and also specifically the ones that we are covering. I told you, I referred you in the back, the inside back of your book, you will have a table with all the metals, important metals, and with their crystal structures. Okay, so let me continue. Don't interrupt this. Once we are finishing with something, then interrupt better. So we have 0 there. 6 over 2 becomes how much? 3. And plus 1, which is there. So the number of atoms per unit cell is how much? Is 4. So we have determined that. Okay. Number of atoms per unit cell is 4. So that we got. Atomic weight we get from the table, that we have. Avogadro number we have. The only remaining thing is this, which is the volume of the unit cell. You can put a U here. It's the unit cell volume. In the previous one I have corrected that. Here I forgot. So the volume of the unit cell. What is the volume of the unit cell? Of course, this is a cubic. The volume of the unit cell is how much? In the cubic cell, how much is the volume of the unit cell? It's equal to A cube. Remember? صح ولا لا? We said in the cube, it is A by A by A. That's the cubic crystal structure, right? It is, since it is a cube, so it is A, lattice parameters are A by A by A. صح? That is the volume of the cube. But we don't have the value of the lattice parameters. We have the R value. We have the radius of the atom. So what can we do? We find the relationship between the A and R the same way we did in the previous, for the previous crystal structures. We find the relationship between R and A, and then plug in and then we say the volume is equal to, the volume of the unit cell is equal to A cube. We plug the A in terms of R and we cube that. So for the face center cubic crystal structure, what did we say? Okay, I don't want to go through this again. I will show you what we have done. Remember, we developed this equation. We determined that. We said this is equal to H, sorry. That length we said is equal to H. I already did this with you. Let me do it again. ما في مشكلة. We said if this length is equal to 1R, 2R, 3R, 4R. So basically this is 4R. Okay. And then from there, we can say this is the hypotenuse. هذه شو نسميها ذي بالعربي? We call it something like that. And this triangle, hypotenuse, 4R square. This is A and this is A. So A square plus A square from Pythagoras, Pythagoras, is equal to 4R square. So basically 4R square is equal to A square plus A square. يعني كم؟ يعني 2A square. 2A square. And if you get the square root of both sides then, so 4R will equal to square root of 2A. Basically what we are having here. Very simple. Now from there, you can say A is equal to 4R divided by the root of 2. You just cancel A here, bring it there. A is equal to 4R over square root of 2. And this is what we are having here. A is equal to 4R divided by square root of 2. Basically, the volume is A cube. Then therefore, this is A in terms of R. So you can say A cube is equal to all that cube. And since we have the R, actually, the R is equal to 0.128 nanometer. And since we normally get the density in centimeter cube, basically the unit, so we can convert this to centimeter. It's 1 nanometer is equal to 1 times 10 to the minus 9 meter. And it's equal to 1 times 10 to the minus 7 centimeter. So basically you use that number here for the R. Plug in that number for the R here, and then cube the whole thing. You will find the unit cell volume becoming that much. Plug in this number in this instead of the VUC here. The others you have, plug all the numbers there. What you are going to get will be this number, which is 8.89 grams per centimeter cube. If we compare, if you look at the experimental value, which is this, we are putting it here. If you compare it to the experimental value, you will see a very negligible difference between the two. So basically, we can say very clearly that theoretical density we can calculate with just the knowledge of the crystal structure. Sitting on your table and holding a pen only, and if you want a calculator, and just plug in the numbers from the knowledge of crystal structure instead of going to the lab and determining the densities of the different materials. You can do that using the knowledge of crystal structure. Any question? Shabab, any question? Are you with me?
دكتور ممكن يكونوا متساويين
شنو يعني متساويين؟
الاكسبيرمنتال هي ثيوريتيكال.
يعني سؤالك شوية ما أدري شلون، يعني شنو ممكن يكونوا متساويين؟ في شيء الحين أنت لما تشرب تسوي لك كوفي، سوي كوفي، أنت تشرب كوفي؟ تشرب كوفي أنت ولا ما تشرب كوفي؟ جاوبني.
لا ما أشرب.
ما تشرب كوفي، إنزين. يعني شنو تشرب؟ شاي؟
إيه شاي.
زين، افرض ان انت سويت شاي حقك بروحك، يعني بس سويت لك شاي، هاي الجلاس الشاي تحط فيه شكر صح؟ وتحط فيه شيء انت تحبه مثلا. هاي الجلاس الشاي اللي تسويه، do you make that cup of tea which you are making؟ انا اسوي لي كوفي بصراحه. مع انه مو شرب كوفي بس يلا when I'm hungry I drink coffee at work only. اذا بسوي لي كوفي الحين وبسوي لي كوفي عقب نص ساعه، هل بسوي نفس الكوفي بالضبط الانجريدينتس؟ تعتقد؟
لا.
مقارب ممكن، لكن هل نفس الشيء؟ هاي جلاس كوفي انت قاعد تسوي، ما بالك لما بتسوي calculations فيها details، كل هاي details all those details are there between the experimental. In the experiment you will use there are different error sources صح؟ and the scale and the maraschino and the water you will use to determine all those will be different from, so numbers cannot be really يعني the same except if there is a coincidence only because of the differences that in the different materials and the different tools and all those are different. That's why احنا في حصه يقول our group will be ready. Anyways, so what we say, no, they cannot be the same except if you have a coincidence, because there are different sources of errors in each one of them, in the calculation and in here as well, and accuracy that you could be using. Any other question? Okay, no question, then we are going just to look at further the density, since we are talking about densities. So here we said, previously we talked about that.
دكتور عندي سؤال.
يعني أنا طوفت الحين، لا طوفت الحين ترجعني علشان تسأل السؤال، اصبر لما أخلص النقطة. So we talked about the densities. We said densities of metals are bigger than the densities of the ceramics and bigger than the densities of the polymers. This is basically due to what? First of all, we know that the densities of the metals are higher than the densities of the rest of the materials due to the three reasons we have covered at the beginning of this chapter. We said metals are more dense than the other metals because of what? Because we have only basically one type of atom there. The second, the metal's type of bonding is not directional, so that it can adjust itself to increase its packing. And the third reason was, and that is general for all materials, is that they have basically the knowledge that the material lowers its total energy to its least. That is what the material does, so it goes to the least energy level, closest position, to reduce its total energy. These were the three reasons. In addition to that, so this is what I'm saying here also, they are close packed, yani packing is better because of the metallic bonding is not directional. But in addition to that, we also need to add one more thing, because we know now about the densities. They have large atomic mass. The metals have large atomic mass compared to the ceramics, for example. Ceramics are less densely packed because the bonds there are ionic, and some covalent character as well could be there, but often lighter elements would be there. For example, يعني مثلا you say magnesium oxide, so it's an oxide, there is an oxygen there as well, silicon oxide, and so on and so forth. So you have an element which is lighter, so basically densities are lighter there. The polymers have poor packing because basically we have a lot of them are amorphous or semi-crystalline, so you have gaps there in between, and generally they have lighter elements like carbon, hydrogen, and oxygen, and that's why you have the metals with much higher density. So this is why we refer to it as a more dense material than the other ones. Composite materials, it depends on the, yani we say it has intermediate values between the high metals to the low polymers, but it depends on how we design the material or the composite material there. Yes, tell me your question now. No
دكتور
question.
الجدول احنا بنكون عندنا في الامتحان والله المعطيات بتعطينا اياهم.
Either I will give you the table but not with all the information. I crossed this, صح? I told you I'm not going to give you these. كنت واضح كذي. If I will give you, I can give you copper with atomic weight, with the number, with the atomic radius, for example, but not these information. I wouldn't tell you that copper is FCC. I wouldn't tell you, for example, the aluminium is FCC. I wouldn't, any material, gold, that it is FCC, or if it is BCC, for example, the barium. I wouldn't tell you that. No, those will not be given to you. Though also, I don't want you to cheat from the number there. You would say this is the density and you get it. No, I wouldn't give you those. If I give you something, I'll give you the atomic number and the atomic weight. Of course, this is no problem to give it to you. Or I can give you the problem without a table. I just give you the material. I'll give you the atomic weight, that number, for example, and I give you the atomic radius, مثلا. So I could do that. All right?
تمام دكتور.
Now I already told you at the beginning that we don't have only those 4 types of crystal structure types. We have more than 14, actually more than 16 different types of crystal structure. Let's just, for the knowledge, we look at the different types here as a summary. We have the simple cubic crystal structure. We already have seen that. The body center cubic crystal structure, you have a body center there, it is cubic. And we have the face center cubic crystal structure. So we already have covered these 3 already. You have the simple tetragonal. The simple tetragonal is different from the simple cubic in that this dimension is different. The longitudinal dimension is only different. So this is called simple tetragonal. We have the body center tetragonal. Again, this is a tetragonal. You just have a body center, an atom in the body. There you have. Then we have the orthorhombic, simple orthorhombic. Orthorhombic is different than this in that you have those 2 dimensions becoming different. So you have this and that and this. The 3 dimensions are different. We have the body center orthorhombic. So you have a body center, you have an atom in the body. You have, this is a different one. You have a base center. You have atoms in the base, as you could see. It is orthorhombic again, and the same as the simple orthorhombic, but you have atoms in the base, basically. That is why it is called base center. You have face center orthorhombic, rhombahedral. You have hexagonal. Of course, this is not correct. We already covered the hexagonal, right? And it does not look like that. It is a hexagonal prism. You have the simple monoclinic, base monoclinic, and you have the triclinic as well. So these are examples of the different. Of course, not all of them are of interest to us because we already covered the most common ones. We said the BCC crystal structure, the body center cubic, the face center cubic, and the hexagonal closed pack. Those are the most important ones for the metals, basically, the most common one. Even the simple cubic is not a common one. As we said, it is rare. Only polonium, which I know, displays this the simple cubic crystal structure. This is for your knowledge that we have much more there. We will see more on the crystal structure when we go to chapter 9 as well. Some phases would display, for example, the orthorhombic crystal structure. We will see which one are those. Another knowledge that we also require when we go to chapter 4 and 9, we need to understand what is the meaning of polymorphism. Polymorphism is the behavior of a material, basically. The word poly here, let me change the color in order to have a nicer color for you to see better. So we say poly, and we are used to this now. When we say poly, we mean many. And then, so this poly means many, like polymer. So poly means many, mer is a unit, so many units. In the same way, now here poly again means many. Morphism, polymorphism. Morphism comes from the word morphology. Morphology is basically the crystal structure. This is what it is. So when you say polymorphism, yani many morphologies, many crystal structures, and this is a behavior. We call it also allotropy, but basically we better use the polymorphism much. We normally use this word. What does it mean? It means that there are elements or there are materials which display different crystal structure, polycrystal structure, polymorphism, different, many morphologies, many crystal structures with changing the temperature or the pressure, for example, because we will need this in chapter 9 specifically. For example, carbon does not have a unique crystal structure. It can exist as a graphite at the atmospheric conditions, and the graphite has a very beautiful crystal structure. If you could see it there, you can go through the internet, just look at the crystal structure there. So carbon can exist as a graphite, which has a specific crystal structure, and it can exist also as diamond. What is diamond? It's basically carbon, and this carbon, but the crystal structure in diamond is very complex crystal structure, and it gets developed at high pressure. And now this is what we are saying: at high pressure, because of the pressure, the crystal structure changes. So carbon is a polymorphic material. It can display different crystal structures at different pressure. Iron the same way. Iron is also as a polymorphic material. Why? Because it will have a BCC crystal structure at room temperature, for example. If you raise the temperature, as we are going to see that in the phase diagrams in chapter 9, at just above 912 degrees centigrade, that is degree centigrade, so above 912 degrees centigrade, the crystal structure changes from the BCC crystal structure to an FCC crystal structure. This is the normal behavior of the material. So as you can see there, with changing the temperature, you see the crystal structure of the material change. So iron is another polymorphic material as well. So this is what polymorphism means basically. Next, we want to also understand this issue of single crystalline and the difference between it and the polycrystalline material. We already talked about that at the beginning of the course, but we are now going to formally address this and see why do we produce single crystalline materials and polycrystalline materials. Single crystalline materials, for a single crystal, what is the meaning of that? When the periodic and repeated three-dimensional arrangement of atom is perfect and extends through the entirety of the specimen without interruption. There is no interruption. The atoms are all arranged periodically in a 3D without any interruptions there. Of course, this is contrary to what we have in polycrystalline materials. We will see this requires actually complex growing techniques, and it is expensive to produce. It is used in electronic microcircuits and employing single crystalline, for example, crystals of silicon in turbines as well. We will see in a minute that. But on the other hand, the polycrystalline materials, it's a collection of many small crystals or grains. So a crystal is a synonym to grains as well. Small crystals, nuclei or nuclei grow in several locations and meet at the grain boundaries. The grain boundaries there split or distinguish the grains from each other. Let's look at how polycrystalline materials get produced to understand what is required to produce a single crystal material. And if we understand how the polycrystalline materials get developed, then we will understand what do we require to produce a single crystal material. So normally, in cooling down any material, so let's say we have a material there, okay, and it is molten metal. So this is molten يعني شنو؟ molten يعني مذاب. Molten material. So this molten material, if we normally, in the casting, for example, we go and cool this down. So as this cools down, what is going to happen? This is molten, يعني معدن مذاب. This is liquid. As we cool down, do you expect the solidification will take place in all the material at the same time? Of course not. Why? Because the temperature in different parts of the material are different. So where will the where will the first solid is going to develop? In the coolest place in the material. Let's say for example here, in the coolest place, the first solid crystal is going to nucleate, and then in the second place, and then in the third place, and then in the fourth coolest place, and then there, and then there, and then there. So it's not happening at the same time. And since it did not happen at the same time, in this place, for example, the atoms are the crystal nucleates, and the atom will be oriented in certain specific direction. In the second place, where the solid nucleated, the orientation of the atoms will be different from that, and the orientation of the atoms here will be different from those, and the orientation of this and that and this and this. Everywhere nucleation happens and the crystal develops, and this is the first stage, which is called the nucleation of the solid crystal. It happens in different places because of the difference in the temperature. Once the nucleation happens, then it is going to grow. Every one of these is going to grow bigger and bigger and bigger in different orientations. Basically, the atoms in every crystal is oriented in different ways. So they are going to grow bigger and bigger and bigger, as we could see there, until they impinge against each other with a different orientation. There is a mismatch actually between the orientation of these atoms and the orientation of these atoms. So therefore, there is an imperfection here happening, and these imperfections between these is actually the bonding is not perfect there, because the orientations are different, and that's why the material develops, different crystals there. So you have a polycrystalline material developing due to that, and these surfaces between a grain forming and another grain, which are there, which I'm showing, are called the grain boundaries. These grain boundaries are imperfections happening naturally in the material, because this is what happens naturally. We are cooling down naturally, and without any control, naturally, polycrystalline material develops in the material. You have different crystals or different grains developing in the material. Does not develop single crystalline material, does not develop naturally in material. Therefore, in order to develop single crystalline material, basically, what do you require? You require actually, and that is expensive, as I am, you require a complex growing technique which will ensure that you have same temperature everywhere, and that's why a bulk of material is not used to produce single crystalline material. Layers actually are used to make sure that the temperature everywhere is equal and the crystallization is done in the same orientation in order to produce one crystal without the grain boundaries occurring in the material, and that is a crystalline material.
دكتور تايم زاب.
Examples. نعم.
تايم زاب دكتور.
Oh, time's up. I will take another few minutes and I'll finish this. Okay. One thing about single crystals, for example, it's used in many engineering applications which require single crystals. Especially the single crystalline materials are used in high temperature applications. Why? Because basically the grain boundaries, as I said, these are imperfections. The bonds there are not as strong as within the grain. These are weak parts actually in the material, and that's why at high temperature it becomes weaker. So for example, in turbine blades, for example, you want to use single crystalline material, because as the temperature increases, those grain boundaries become a source of weakness in the material. Also in single crystals for abrasors, for example, or abrasives. If you want to cut, let's say, materials, you would use single crystal materials instead of using poly material. One question I will put for you. You have diamonds, right? Jewelry. that we use normally. How the diamond, what do you use to cut different materials? The hardest material is the diamond, so use diamond to cut the other materials. What do you use to cut diamond then? Think about that question. We will answer it next lecture. I will put it for you there. Polycrystalline materials, most engineering materials which we use are polycrystalline because it is simple, inexpensive. If you want to use single crystalline material, it is expensive to produce. Unless you have to use single crystalline material, you wouldn't go for that because it makes life more difficult, more expensive basically. Also, they are called multi-grain systems. Each grain is a single crystal. So this is one crystal, which is one grain as well. And the grains could go small, very fine grains, coarse grains, and it could go also ultra fine as well. This is my last page. I'm going to finish today. Also, one notion, I wanted you to understand the difference between isotropy and anisotropy. And what's the meaning of isotropic material? Isotropic materials are materials which have properties independent of direction. Yani, if you change the direction of the loading of the material, the property of the material will not be different. Anisotropic is opposite to that. Anisotropic means opposite, that prefix, which means that opposite of isotropy. The physical properties vary with direction of the material. So in single crystalline materials, the properties of single crystalline material depend on the crystallographic direction. For example, if we look at a single unit cell in the BCC crystal structure, the modulus of elasticity in this direction is different than the modulus of elasticity, the stiffness of the material, in the diagonal direction. This is 273. This is 125 gigapascals. So why it is different? Well, because you have the different bondings are there. These are 3 bonds here. There are 2 bonds here. So you have, this is what we refer to anisotropy. The physical properties differ with direction, and that is what we refer to as as anisotropy. It's not this one, okay, as anisotropy. But generally, the polycrystalline materials display, they have, let's say this is a polycrystalline material. If we look at a single crystal, the single crystal, of course, because the atoms are orientation are in certain preferred direction. It is the orientations of atoms are in certain preferred direction. So it will have properties in this direction different than properties in that direction. But this is for a single crystal. If we have polycrystalline, this is a polycrystalline means there are many crystals, and these crystals are randomly dispersed in the material with the different random orientations of the atoms. يعني عندك انتشار عشوائي للatoms للcrystal, and therefore انتشار عشوائي for their orientations as well. This basically random orientation and dispersion of the crystals there makes the material to be isotropic. And not because that each crystal is isotropic. Each crystal itself is not isotropic. It is anisotropic. But also for some polycrystalline material, if you stretch the material, for example, like this, if you stretch it in this way, yani let's say we stretch the specimen and we look at how the grains look like, they will be elongated in this way. So this is caused by elongation and the flipping across the crystal, the grain boundaries. This causes the material also to be anisotropic there as well. So this material is now anisotropic. Properties in this direction are different than the properties in this direction. I'm done with this. I will stop the recording. Sorry for taking more time today, because we had to finish this chapter today. Let me stop the recording.